So there are lots of different data types, and I apologize in advance. This is going to be a very technical talk, so hopefully people are in the mood for that. There's some high precision data types, single, double. Everyone knows that. This is an HPC conference after all. And there's all these machine learning, lower precision data types, which people have been learning about as well. And why would you want to use lower precision? Well, it's less power or it can be faster. And so the big question in this talk is, in what circumstances can we use lower precision instead of higher precision, maybe to get some acceleration in our application? And there are two most commonly used methods. There are a whole bunch of efforts and partial papers or partial results, but I'm going to at least just mention these two methods. The first method is iterative refinement, and it's the idea of using linear system solves. It's not, it's benchmark related. It's not really practical. In other words, you use a preconditioner of the LP solve itself, but you could do something better if you knew what you were talking about, but that's another talk. And there's the other method, which is combining lower precision together. So you just take a bunch of a high precision element and you just write it as a sum of lower precision elements. And then you do your work in lower precision. And then pay attention to these things. All right, so some notes about iterative refinement. There is this benchmark out there. It's very much just a benchmark, and that's it, because there's a much faster algorithm that could be used, but that's kind of another talk. At any rate, what it does is it takes this matrix in high precision, double precision in this case, and it lowers it to a lower precision, and then it just iterates on the answer until you get the final result that you want. And you may wonder why. I mean, people have known about iterative refinement for years, and there's some really great papers by Hyam and on some NVIDIA hardware and other things that talked about using this technique. But why didn't why aren't there other papers to talk about eigenvalues or something like that? Why just linear system solves? And the point is that it's a rather different situation. So this is a special case where people use lower precision. So I just mentioned it for the sake of clarity, for the sake of completeness. All right. Now, what is the good and bad of using lower precision? It can be faster, less power. We just saw Sanjeev Shah show us a slide where, over time, you saw the acceleration of the lower precision kernels going faster and faster relative to the standard single and double. And I think this is the standard going forward. You will see double precision won't accelerate as much as, say, a lower precision might accelerate. So for things like matrix multiply, you can amortize the conversion time into a different precision, and so it's effective. And so people talk about it in terms of GEM. Of course, it applies to other things as well, but people love to talk about GEM for that reason. The conversion time, of course, might be prohibitive if the work isn't large enough. And you also notice that many vendors are starting to support lower precision. It isn't just, we saw that slide earlier where you saw those acceleration. Of course, that this is happening on some other GPUs as well. So at any rate, if you're doing this lower precision stuff yourself, it can be tedious, but you could do a replacement. All right. So the easiest solution for testing lower precision is just to take a higher precision API and put in the kernel underneath the covers a lower precision variant. And I'm going to give you a dummy example here. No one would ever do this, but you could do it. You could take a DGEM, which is a double precision matrix multiply, and you could do all the work in single precision. You just convert A into single precision, convert B into single precision, do your multiply in single precision, and then upscale back and convert. And that would be easy for an application developer who didn't know whether or not their application actually needs single or double precision. They could just call this kernel. They don't have to change anything in their API and try it. But it may not work with every application. And I've done experiments with HPL, not necessarily using single precision here, but using really lower precisions as well. So the concept in this talk, or what's going on here, is that high precision can be written as a sum of low precisions. And really, if you look at floating point, all it is a sum of powers of 2. And there's an exponent, which is the highest power of 2 that it has, and then the mantissa, which is the number of bits it's tracking. And so I give two examples here. You don't know what the mantissa is, but you know in the second example, the mantissa has to be at least 6 because it's covering 6 points if you don't want to have any errors. Now, if you imagine that you take something like a 6 mantissa problem and you try to write it as a 3 mantissa problem with the lower precision data type, obviously you need to use several lower precision data types and write it as a sum because there isn't enough precision in the lower precision to hold the whole thing. So that's essentially what I'm talking about. And you can do the same thing with matrices as well. So in 2019, we did this with FP32. We went ahead and we wrote an FP32 matrix as a sum of B float 16s. And I just denote that B float 16 times 3. And we let A0 represent the most significant bits, A2 represent the least significant bits. I'd continue using that notation. So whenever I've heard an A0 in this talk, I mean the most significant bits. And whenever it's A10 or A5 or whatever, I'm referring to the least significant bits. Okay. And instead of doing A times B, you can now do this product of 3 sums times another 3 sums, which is either 6, 9 multiplies 9 if you want to be robust, 6 if you just want to be lazy and get the result as fast as you can and maybe get an approximation. Another thing to notice, though, is that, so in this case, I take a matrix A and I break it up into 4 parts. I take a matrix B, I break it up into 4 parts. And I'm assuming, if you're not familiar with the GEM, that's fine, but GEM has these dimensions M, N, and K, where all the A's are M by K and all the K's are K by N. You might have some transposes in there, but essentially that's what we're talking about here. And if you look at this and you write this out, there really are 7 bins here, 0 through 6. And the bins correspond to the sum of the indices, right? So bin 6 is A3 times B3. I'm going to call this 16 multiplies. Why? Because I don't want to pull wool over anyone's eyes. But notice that you can actually do this in 7 gem calls, 1 for each bin. So you can just sort of stack them together in the right way, and you put A in one direction, put B in the opposite direction, and then you can do all your multiplies in 7 gem calls, but it's really 16 multiplies. I hope that notation or that description is going to make sense to people. So I'm going to continue calling the 16 multiplies, but in practice, when you implement it, you'd be a fool to do it that way. All right, so the summary for matrix multiplication, again, I have to talk really fast. I have a lot of data here, is you have this sum of these lower precision matrices that you're adding together. You can assume that there's a scalar in front of each one. That scalar can be either a diagonal matrix, or if you assume that everything has the same exponent in the whole matrix, it can be a constant, or you can even assume it can be a constant diagonal to accomplish the same thing. But the truth is that those little scalars and things like that can be done outside of the gems. And so they really don't matter. And so sometimes I use them, sometimes I don't. You'll just have to forgive me. It's kind of notationally awkward to throw a whole bunch of scalars in every single equation everywhere. So sometimes I drop it just to make the talk easier and quicker to understand. The other thing is that you want to sum up the results going from the least significant bin to the most significant bin. And that's done for accuracy. Everyone knows that when you sum up a bunch of floating point numbers, you want to do it in lowest to highest order. All right, so if X and Y are vectors and you are doing fixed point conversion, so I'm talking about a specific type of low precision, I'm talking about fixed point now, or block floating point if you like. And notice that if you're only tracking a certain number of bits and the floating point number contains way more bits than you can track, you're going to drop bits. And that's just the reality in the conversion, especially since it's fixed point. You have shared exponent, which means that you're very likely, I don't know about how likely, but you're very likely to come up in situations where you have to drop bits. Now, you can still write it as a sum of lower precision parts as long as you have some scalars that can keep track of those extra locations. So that way you're monitoring the right thing. Another thing to look about this data lost in the conversion, you can actually track how much data you lose, excuse me. And so that's nice, and you can exploit that. This is an implementation detail. I won't get into too much things, but I will say that you want to make sure that during your conversion, all the errors are moved to the very end. Sorry about this. I think it's spam. it's not always relevant that you move the errors to the end, like B float 16 with 3 splits, but the conversion, that the last term should have the maximum error, uh, and there shouldn't be errors in the terms that come before it. And it really depends on whether you're using low precision as floating point or low precision as fixed point. If you're using low precision as fixed point, you just have to make sure that there's no errors in your splits. Otherwise, you're okay. If you're using low precision, if you as floating point, though, you have to make sure each split is done error free for obvious reasons. So the conversions need to be done very carefully. I actually, it's kind of funny. I wrote a code, or I created a proof that said, okay, the accuracy you expect is this, is the best case you can get. And then I wrote a tester to verify that all my conversions actually achieve that accuracy. And yeah, so the thing that you can do, though, is that you can make sure that those conversion operations can all be done in vector arithmetic. This is on Xeon, obviously. So conditional ifs and FMAs, all that stuff can be utilized. And I created a whole bunch of AVX 512 kernels that do these conversions that you need to do, and they seem to work well, and they seem to work fast too. So let's talk quickly about errors. It's kind of interesting because if you're doing a linear system solve, then orthogonality is fantastic. You'd love orthogonality. It has a condition of 1. It's the best case you could have. When you're doing dot products, orthogonality is the worst case you can have, because the dot product of two orthogonal numbers are going to be close to machine epsilon. Our two orthogonal vectors are going to be close to machine epsilon. So the thing that is interesting here, and the thing that's new here, is notice we have all these bins where we're adding things up. If you have significant cancellation error and significant absorption error, you will sometimes see zeros in bin 0. And if that happens, you can see it and you can notice it. And you can actually do proofs that say if there are no non-zeros, if there are no zeros in bin 0, then you can prove that you have achieved a certain kind of accuracy. Now, this sort of thing you could also do with a regular gem, but there's no notion of a bin 0 versus, there's only one bin when you're doing a regular gem. So anyone could do this, and you could do this sort of analysis after the fact with gem as well. But it's convenient to do it here because now you can make a really smart code, so to speak, a code that actually finds where there's problems and then does something different. And so I think that's an important point. Another important point is, can we come up with a heuristic method, not robust necessarily, that can give you an approximation to SGEM or DGEM or even QGEM, where QGEM is like quad precision? And the answer is yes. And so that's the point of the talk. And since we're using fixed point, can we address problems with high cancellation error and denormals? And the answer there is yes. And I have specialized tester that test very high cancellation errors, and the results are just fantastic. In fact, I would say that the methods that I propose in this talk actually get more and more stable compared to floating point. Obviously, if you have high cancellation error, both floating point and these methods, they both will have less accurate results. But comparatively speaking, if that makes sense, these methods will be better in general, on average. If you assume uniformly random data in the conversion process. Okay, and so can you detect spots where the relative errors are high? Yes, you can. If you look at bin 0, so that's something new that we sort of found on our own. There are lots of work that's been done similar to this. And can you put an upper bound on the number of operations of the input range? And the answer there is yes as well. So that was kind of nice. And can you leverage these machine learning processors that are coming out that do fast, lower precision to get a result comparable to calling SGEM or DGEM? And the answer again is yes. Will you have the most robust and accurate method known? And of course, the answer is no. I don't want to fool anyone. The answer is no. Sometimes floating point will be better. Sometimes these other techniques where you break to lower precision will be better. You can talk about averages and things like that, but that's the only thing you can do. So the general idea here is to take some high precision and break it up into low precision. There'll be some scalars or matrices, either way, depending on how you want to look at it, whether you're scaling by rows or if you're scaling A by every single row has its own shared exponent, or the whole matrix has its own shared exponent. I recommend every row have its own exponent and every column for B have its own shared exponent as well, or maybe shared amongst those. And the gem in lower precision, the idea is that it has to run much faster than the original gem. So you copy A and B into these cascaded, a sum of low precision matrices. You do multiple gems at the lower precision. This is assuming high precision accumulation. I don't want to overlook that detail. Then you sort of glue everything together, and you may use high precision there as well. It's not necessary in some cases, but assuming since this is a TAC supported conference, that everyone's familiar with the UT Austin work of Bliss. And so I wanted to work with Bliss, as Sanjeev Shah mentioned. We like open source stuff a lot. It's an open source BLAS package that has mixed precision. And I wanted to use this because of the fact, well, I wanted to use it because it was open source, but I, I did something interesting. So I didn't take double precision or single precision and move it down to something like int 8 or bfloat 16. What I instead did is I took quad precision or double double and cascaded it down into double precision. And I did that because I wanted to use Bliss. Essentially, I wanted to actually call Bliss kernels, not create new assembly kernels. There's no assembly in this talk. The conversion routines are vector intrinsics. They might as well be assembly. So maybe I'm cheating by making that statement, but there's no assembly in this talk. And so we targeted Bliss for this reason, so we could use it and we could demonstrate these results today. And we're actually still using fixed point though. We're just storing it in double precision data. So that's kind of interesting. And so again, the general idea, I keep want to bring things up at a high level. Whoa, I'm going the wrong way. All right. So the conclusions for QGEM from the paper that we have that's still pending at Tom's is that the best known method, there's Ozaki BLAS, I think they're sometimes called OZ BLAS, and we're twice as fast as them. So these are very good results, and I'm quite proud of these results. And the other thing you should notice about this is that we get to our peaks, or we converge much faster as well. And again, that's because we spent a lot of time working on that conversion and making it as fast as possible. If you have a really naive conversion, it's just plain old C code and you're converting element by element, you're not doing it in a vector fashion, it can really slow down your code. So we did things right. We implemented it right, and we got fantastic, absolutely fantastic results. And so you see, this is time slower than a Bliss DGEM. And of course, this is quad precision emulation. And so of course it's going to run slower than a Bliss DGEM. But double tends to run about 20x slower or 30x slower. So what you see here is some nice results. And we also tried it on extremely low condition data. And so I just did a whole bunch of data points, ignore the x-axis. It's just a whole bunch of data points on hundreds of thousands of matrices, hundreds of thousands of relative errors compared. And this is a really highly ill-conditioned system. And so you can see that the accuracy is not fantastic for quad, but it's a whole heck of a lot better on average than double was. And I want to move past this slide because, again, I have a lot to say. So another thing we played around with a lot is mixing and matching. You can use int 8 as lowest precision, but I will say this work is not new. Ozaki has done similar and great work. And there's been a number of papers on NVIDIA as well. And so you check out those results. And I will also say that the conversion time is very fast, but I will also say that we assume for the talk, sometimes I assume one shared exponent per matrix, but in practice, I'm doing it at one or more shared exponents per row of A or column of B. All right, so the accuracy has to be really accurate on the splits. And there are cases where you can get arbitrarily bad results. Just sort of imagine you have really small numbers in the middle and your fixed point can't hold those bits. And so they underflow to zero. And you can get arbitrarily worse results than floating point. That's just the truth of this method. And if you also have a number of multiplies, depending on how many splits you do. So how many bins you have a different number of multiplies. And you usually have on the order of z squared or maybe z squared over 2, somewhere between those two extremes. And so if you're just splitting down into int 8, I sort of noticed that 3 or 4 splits is good for approximating SGEM. If you're splitting down to int 8, 6 or 7 splits is a good approximation for DGEM. 13 to 15 splits might be a good approximation for some quad or double. And is it better to have more splits or more multiplies? Not necessarily. So I just sort of talk about the number of multiplies, and the splits is better, definitely. And then the mixed precision and gem. So Bliss is an elegant solution. Again, I'm assuming everyone's familiar with Bliss because this is a tax-sponsored event. But if you're not, look at it up. My favorite example is you take A is, say, B float 16 and B is FP64. What Bliss would do, it's the first library that did mixed precision in open source ever. And it would convert B to B float 16 times 7, and then you could do A times B with 7 B float 16 gems, as long as it's faster than 7 times a call to, as long as it's faster than 7 D gem, as long as, I sort of had this equation backward, as long as 7 B float 16 gems are faster than 1 D gem call, you will make a win. And that's always good. Another thing I want to point out is I did lots of different types of testing, widely ranging, uniformly random, ill-conditioned. I have special ill-conditioned generators that really test the ill-conditioned results. I don't know if the legend is available, but this is just a whole bunch of different single precision approximations where you have different splits, different number of bins, different number of multiplies. And I believe the orange line is single precision, and this is overall accuracy. I wanted to do this on low conditioned and high conditioned because the results change. One of the things you notice is that some of the results that have a large number of splits start doing really well. The numbers that didn't have as many multiplies, they tend to do really badly as you increase the time. So again, you have this you can sort out the results in higher precision. It turns out this doesn't really help a lot, but you can. So I'll skip past that and I'll just jump to my conclusions because we're coming to the end of the time. And on SPR, we picked some random dimensions between 16 and 768. This is no border cases yet. It's just prototype code, sorry. SGEM in these cases still gets a high percentage of peak, and we use int 8 either signed or unsigned in conversions. And what we found is that we were faster than SGEM between 1 point up to 1.5 up to 4x faster than SGEM, depending on how many splits, how many multiplies you want. And so that proves this technique is very promising. And so again, you can beat SGEM or DGEM. So imagine a world where all your gems or all your routines can track an arbitrary number of bits. And so in this case, think splits. And an arbitrary accuracy. In this case, think the number of bins. And you could experiment with precision and speed. You could change it up. And while Bliss was the first open source package in mixed precision, you could also do mixed precision in a much better way than was done in Bliss. And so you could beat the best known method out there. Anyway, I'm told I should stop at 9:25, which is like now. So, or 11:25. I forgot I'm on Central Time. I apologize. I'm on Pacific. So, but this is my email. If you have things, we do have a paper under review at Tom's, and there's a lot of implementation issues that I sort of weighed my hand over. If you'd like to more details or have considerations, please ping me and let me know about it. Okay. Any other questions or thoughts, or I'm way over time, so.
Thanks, Greg, for a great presentation. This is a time for questions. We have 4 minutes of window. Are there any questions to Greg? And while the questions pops up, so yeah, there is one question by Benson. The question is, any possibilities of standardizing this? IEEE arithmetic enabled much portability, but perhaps open source portable libraries are sufficient.
Well, we originally targeted Bliss for that reason. But Bliss also did a major review, is probably people attack no. Bliss is just do this Bliss 2.0 that's just coming out. And so we do not have this in Bliss at as of today. But that was the reason why we targeted it. I mean, as Sanjeev said, we're about open source. So that was the reason for targeting this work in that environment. That was the whole reason to go to Bliss in the first place. Plus, they're really great people. So that only helps as well. But I think, yes, we would like to open source some things at some point. That would be nice to find that venue for that. Yeah.
Thanks, sir. Any other questions by the attendees here? As the questions pops up, I have a query regarding how, do you have any examples or how to use or leverage your technology to do the emulations and then see the differences? Like how one should start with using the reduced precision.
Yes, but not in this slide deck. So, I'm sorry. I was thinking of throwing in some backup slides, but then I thought, no, that just gets too confusing. And what if people have questions on the backup slides? And yeah. So I think that's an excellent idea, and I'm going to take that as positive feedback going forward. I hope that's okay. But no, I
Yeah.
don't have. I don't have a chart I can show you. Um, but you can sort of imagine. I mean, there's lots of application programmers here. If you're using double precision in your application, the real question you should be asking yourself is, do you really need 53 bits? Could you get by with 40? And you
Right.
wouldn't use 40 in any other way. You wouldn't be able to use 40 with single precision. Single precision doesn't do 40. But with a technique like this, you could actually try 40 bits of act, to see what it does. See what it does to your application.
So I can understand the precision loss at lower precision, but are there any performance overheads? How much do you estimate or see if you bring down to the lower precision, doing the calculations and maybe getting back the results in high precision?
Well, one of the things that we've paid a lot of attention to was the conversion process, trying to make that run as fast as we possibly could.
Yeah.
And as you saw that when we were comparing to the OZ BLAs, which I think was sort of like a naive fast implementation. And so you saw that we were approaching our peaks much, much faster. And that's only because of that effort to get that conversion. But the one thing I want to point out is that as Sanjeev already showed us, that as we go to future and future processors, these things accelerate. The lower precision keeps accelerating. So while the overheads may always be a worry for some data sets, I would say that the methodology is always going to be promising, and it's going to become more and more promising. It was promising back in 2019 when we did our paper on estimating SGEM, but it's even more promising today in 2025. And I guarantee it'll be more promising in 2030. So the trend is moving in this direction. So if you are aware of these techniques but haven't looked at them closely, maybe now is the time to start looking at them.
Thanks, Greg, for the Q&A. And so thank you, Greg.